So in Gauss law, we talk about electric flux. Now, what do you mean by electric flux? It's a set of electric lines of force. Now, the idea of lines of force itself is imaginary. And electric lines always represent an electric field around a charge. So if we show electric lines really close to each other, then we know that the field is stronger. While if the lines are separated by a bigger distance, then the field is weaker. And also, if the field is uniform, like constant in a particular space, then obviously the lines are going to be equidistant and parallel to each other. So that's the idea of electric flux. So when we get there into electric flux, we see that, let me speed this up, electric flux passing through an area depends on three quantities. The first quantity is the density of field lines, which I talked about just now, showing how close or how distant the lines are, so which is actually proportional to the intensity of the field. Okay? So that's the first quantity that electric flux depends on. Second, electric flux depends on the area. Now, I told you that area is taken to be a vector, and the direction of area is the outward drawn normal. So if this, my hand, is an area, and if I draw a normal this way, that's the outward drawn normal. So let's say that the electric field lines are this way, as shown by my finger, and the surface is kept this way, so which means the perpendicular drawn to the surface is parallel to the field. So the angle is now 0. So here we see that the area is actually perpendicular to the lines, but the perpendicular drawn to the area is parallel to the lines. I hope that's not confusing. The perpendicular drawn to the area is what we are always going to reference. So in this case, the angle is 0 degrees. That means maximum flux is passing through this area. As you can see, maximum flux, all of the flux passes through the area. On the other hand, if the area is kept this way, now we know the perpendicular is that way, outward drawn perpendicular, and the electric lines are this way. So now the angle is 90 degrees, and there is no flux passing through the surface. So what is involved is the cosine of the angle, because we know that cosine 90 is 0 and cosine 0 is 1. So electric flux depends on the area, it depends on the intensity, and on the orientation. So as you can see here, electric flux depends on the density of the field lines, depends on the area of the surface, which means a bigger area will let a bigger flux pass through it, of course, and also it depends on the orientation of the surface, which is the angle that I talked about. So the mathematical formula for electric flux represented by phi is surface integral. That means we integrate over the surface, and actually it's a closed surface integral of the dot product of E and dA, where E is the electric field strength and dA is that little area. So you see it's a dot product, and a dot product is defined as E dA times cosine of the angle, where theta is the angle between the perpendicular drawn to the area and the electric field. I think this diagram clearly brings out what I had been trying to explain. So here you see the surface. This is the perpendicular drawn to the surface. This is the direction of the electric field lines, and the angle is taken between the perpendicular and the electric field lines. So that should be remembered. And of course, the electric flux, phi sub E, means electric flux, is EA cosine theta. Now let me just give you an idea of dot product, or kind of refresh your memory. There it is. So electric flux is the closed surface integral of the dot product of E and dA. And do remember that when you take the dot products, I dot I, or J dot J, or K dot K gives you 1, but I dot J, or J dot K, or K dot I gives you 0. Okay? I hope you know that. So if E is 3I and the area is 4I plus 3K, then E dot A is going to be 3I dot 4I plus 3K. And you only need to take I dot I, and that will give you a coefficient 12, because I dot K is going to be 0. Okay, so in this case, you get 12 units. You can see that dot product is a scalar. It has no direction. So electric flux is a scalar. Although electric field E and area both are vectors, electric flux itself is a scalar. Or here's another example, which is even more easier. If E is 3I and A is 3K. So the electric field is along the I and the area is completely along the K. The angle is 90. So we know that cosine of 90 is what? 0. So even when you use the dot product, you get 0. Here is the case that I've shown, where you have the area represented by the perpendicular and the electric field at right angles, and you get no electric flux passing through that area. Okay? So that's an example of dot product. So now we are ready to understand Gauss's law. So if you have a charged particle, let's say this is a charged particle, we have to imagine a surface around it. It could be any shape. It has to be a closed surface around the charge. And according to Gauss' law, the total flux passing through that imaginary closed surface, the total flux passing through that will be 1 by epsilon naught times the total charge inside the area. Let me go write it. You will understand. So on the left side of Gauss' law, we have the total electric flux. Okay, and we know that the total electric flux is what? Closed surface integral E dot dA, right? So that's what we're going to have on the left-hand side. And on the right-hand side, we're going to have 1 by epsilon naught times Q, where Q is the charge inside the imaginary Gaussian surface. That imaginary surface is called the Gaussian surface. So that's what is coming up here. Closed surface integral E dot dA, which is the flux, is Q by epsilon naught. Do remember, epsilon naught is the permittivity of free space. Permittivity of free space. It has a value 8.85 times 10 to the negative 12. Coming up there. And also, very important, that Q is the charge inside the imaginary Gaussian surface. So if you have any charges outside the Gaussian surface, they do not contribute to the total electric flux. Why? Because you're only looking at the electric flux passing out through the Gaussian surface. So we only consider the charges inside the imaginary surface. Now, all of this is completely theoretical, I know, but it's soon going to make a lot of sense as we try applying it to different situations. So let's go there now. So the first situation that we apply Gauss's law is to a point charge. So let's consider that there is a point charge, Q coulombs kept here. Let's imagine it's a positive charge. So the electric field, as we know, is given by these lines, and the lines are pointing away because it's a positive charge. And then our imaginary Gaussian surface is a sphere. To make things easier, we imagine a sphere around the positive charge with the charge at its center. That's again to simplify things, to make things easier. So that's our imaginary Gaussian sphere. Then we apply Gauss's law. What is Gauss's law? closed surface integral E dot dA is equal to Q by epsilon naught, right? But on the left side, E is a constant. At every point here on the sphere, E is the same. Why? Because it's at the same distance from the center where the charge is. Since E is a constant, it's taken out of the integral. And then what we have is integral dA. What do you mean by integral dA? That's going to give us the total area of a sphere. And the area of a sphere is 4 pi r squared. So now we see the left-hand side becomes E times 4 pi r squared. And on the right side, we have Q by epsilon naught. So now we have put that here. So Q by epsilon naught is E times 4 pi r squared. Rearrange that, and we're going to get E. You see that E is equal to Q by 4 pi epsilon naught r squared. But do you remember that 1 by 4 pi epsilon naught is represented by K, which has a value 8.99 times 10 to the 9. We use that, so you should remember that. So now we get E is equal to KQ by R squared, which means the intensity due to a point charge, rightly so, is inversely proportional to the square of the distance. So the further we go away from the charge, the smaller the electric field is going to be. This is the first application of Gauss law. So here is the second application. This time, let's consider a spherical conductor. So it's not a point charge. We have a spherical conductor, a solid conductor like a steel ball that is charged. Okay? And we want to find the electric field due to this spherical conductor at 2 points. Actually 3. Number 1, outside the conductor. So if this is the conductor, we want to find the electric field somewhere outside. Next, we want to find the field on the surface of the conductor. And number 3, we want to find the electric field inside the conductor. So outside, at the surface, and inside. And you're going to see how easy it is to find these 3 by using Gauss's law. So here we go. So we have a spherical conductor, and we're going to apply Gauss's law to find, number 1, the field outside the conductor. Okay? So here is the conductor. So let's say we want to find the electric field outside. So that's the conductor, the whole conductor. The green part is the conductor that is charged. Charges always dwell on the outside of a conductor. Charges will always move to the outside of a conductor, so you won't find any charge inside. It'll all be on the surface. That's why it's shown on the surface there. And the reason is the electric field is acting out, so it'll push those positive charges and bring them to the outside. So if we want to find the electric field at this point, what do? We now imagine a spherical Gaussian surface passing through that point. And then apply Gauss law. On the left side, we have surface integral E dot dA, correct? And in this case, what's dA, or what is integral dA? It's going to be the area of this surface area, which will be again 4 pi small r squared, where I'm taking little r to be the radius of that Gaussian surface. So here it is. So we have E times 4 pi r squared, where r is the radius, not of the conductor, but of the Gaussian surface. And on the right side, we have Q by epsilon naught. What's Q? Q is the charge inside that Gaussian surface. And in this case, all of this charge is inside that surface. So when we rearrange, we get a very familiar formula, exactly what we got before for a point charge. What does that mean? That means that although the charges are distributed on the surface of the conductor, the charges behave as if they were all at the center of the conductor. Let me say that again. Although the charges are actually distributed on the outside of this conductor, that's the real case, we could just imagine that all of those charges were situated at the center of the sphere. Why? Because we got the same result. All right, now to find the electric field at a point inside. So if we are trying to find the field, let's say at, let me go here. So at this point, we're trying to find the field at this point. So now we imagine our Gaussian surface here. You see the Gaussian surface? How much charge do you have inside that Gaussian surface? There is no charge inside that Gaussian surface. Remember that all the charges are on the outside of the conductor. That means there is no charge here. So what will happen to the right-hand side of Gauss's law? Becomes zero. So when we write that, because the enclosed charge is zero, you're going to have to write E dot dA integral of that is equal to zero, which means E is equal to zero because dA cannot be zero. Oh, that's a very important result. That means although the conductor itself is charged, since the charges are on the outside, there is no electric field inside the conductor. Very important result. Maybe on a day when there is a thunderstorm and lightning, if your car had all the tires stolen the previous night, let it never happen, just imagine. And the car was sitting on the driveway, the metal touching down. But still during that lightning, the safest place on the earth, I should say one of the safest places would be inside the car. Because it's a charged conductor, there is no electric field inside. The lightning is never going to strike you because there can be no electric field inside that car, inside that conductor. For practical cases, do not attempt it, but theoretically, there is no electric field inside a charged conductor. Well, you may ask, what about the electric field on the surface? Isn't that easy? To get the electric field on the surface, we can use this formula, but instead of little r, replace it by caps R, where caps R is the radius of the conductor. Okay? So inside the conductor, the electric field is zero. On the surface, it's kq by caps R squared. And then as you go away from the surface, the little r keeps increasing. That means the electric field decreases. So where is the electric field maximum? On the surface. And then it begins to decrease. So let me show you a graph which will make things clearer to you. So on the x-axis, we have the distance from the center. So that's the center. So here you're moving to the positive side along the radius, and here you're moving to the negative. And this y-axis shows the intensity. So I picked 2 points which represent the radius of that conductor, caps R, remember? The electric field all over here is zero. Look at that green line, that's zero. But all of a sudden, when you get to the surface, the electric field goes from zero to a maximum. And then as you go further away, it drops. Remember, this is not a straight line because it's inversely proportional to r squared, okay? So that is the graph. Another interesting thing is when r becomes infinite, that's only when E would become zero. So theoretically, this graph is only supposed to touch the x-axis when you're infinite distance away. So theoretically, the electric field exists up to infinity, but practically you know that within a few meters, it'll drop down to such a small value that we can neglect it. Got it. The next application is, what if the spherical object is an insulator? So now we have a solid sphere, which is an insulator, and it's charged. Now the thing is, the charges will not be able to be pushed out to the surface. So now you will have a uniform distribution of charge throughout the material, all over the material. Okay, it will spread out uniformly. So we are able to define a new quantity called density of charge. Now what is density of charge? It's the total charge divided by the total volume. The total charge divided by the total volume. We're going to use that, but first Let's find out the electric field outside that conductor. Will there be any difference outside? Think about it before I show you. So it's a sphere. The difference is it has charges all over the volume. But if you're trying to find the electric field somewhere here, wouldn't we have to imagine a Gaussian surface again passing through that point? And wouldn't all of these charges be inside that imaginary Gaussian surface? Yes. So there's going to be no difference when we try to find the electric field outside. The difference is going to happen when we try to find the electric field inside. Because now when you take that Gaussian surface, you're only going to have a part of the charge inside. Well, let's go there. So here you have this diagram, and you can see that for points outside, where I've taken the radius to be r here, it's going to be the same because that's the Gaussian surface, and the point is P. And so for points outside where r is greater than r naught, which is the actual radius of the conductor, of the insulator, you get the same formula, E is equal to kq by r squared. Because, like I told you, the entire charge is enclosed inside. But when you consider a point somewhere here, you want to find the electric field here. So now you imagine that Gaussian surface, and now you know that it's only the charges here that are inside. So first we need to find the fraction of the charge that's inside here. That's where we have defined what is called the the density of charge. Rho is the charge density, or the density of charge. And what is rho? It's just the total charge divided by the total volume. The volume of a sphere is 4 by 3 pi r cubed. So here I had to put pi r naught cube. I'm going to do that when I remember. Therefore, the charge enclosed inside the smaller sphere is going to be the ratio of the volume of that smaller sphere to the volume of the whole sphere, right? So that's what I've written there. So the ratio of the charges, the ratio of the enclosed charge to the total charge will be equal to the ratio of the volume inside to the total volume. So I took this key to the other side. And so I now have the enclosed charge in terms of the total charge. All right, of course, the 4 by 3 pi's get cancelled. And then when you apply Gauss law, closed surface integral E dot dA is equal to E times 4 pi r squared, because that's the surface area of that Gaussian surface, is equal to Q enclosed by epsilon naught. But what is Q enclosed? Q enclosed is Q times R cubed by R naught cubed, which I've substituted here. And now let's make E the subject, because we're trying to find the electric field intensity. So when you make E the subject, you bring this 4 pi r squared here, and you are going to see that you will get r squared and r cubed here. So the r squared gets cancelled out, leaving a r here in the numerator. Look at that carefully, and you should understand. That means the electric field is now proportional to the radius. So inside, the variation of electric field inside is as a straight line, you see, proportionally increasing. Why so? Because as you go take bigger and bigger surfaces, you're going to have more and more charge. So that is how we apply Gauss's law to find the electric field both outside and inside a solid sphere, which is an insulator. Now we come to a very important application. Imagine that you have an infinite plane sheet of charge. So it's infinite, but it's a plane sheet. So charges are arranged in a plane. Imagine there is a lot of charge here arranged in a plane. All right, so this is the plane. It's infinite. And we're trying to find the intensity at a point somewhere here, at a certain distance from the plane sheet of charge. So now what we got to do is First, we need to imagine a Gaussian surface, right? Isn't that what we always do? So this Gaussian surface now is going to be a cylinder that's passing through the sheet, and the curved surface of the cylinder is here, while one of the flat surfaces is exactly that point where we want to find the field, and the other flat surface is on the other side. So that means the cylinder is symmetric. Let me show you the diagram. So that's our imaginary surface. So we're trying to find the electric field due to a plane infinite sheet of charge. Okay, so let me just move this along faster. Okay, there. Here is the infinite plane sheet of charge coming up. Not yet. Here's Gauss law. Oh, I think I need to show you all this together here. So here is the infinite plane sheet of charge. This is our imaginary Gaussian surface. You see, it's cylindrical. We're trying to find the electric field at this point. Okay. So there are two flat surfaces and one curved surface. And these show the electric field intensity. And also remember that the area is represented by an outward drawn perpendicular. So when you come to the flat surfaces, you can see that E and A are parallel. That means the angle is 0. Cosine of 0 is 1. So for the flat surfaces, there is going to be a contribution of the electric flux. But when it comes to the curved surface, we're going to draw the outward drawn normal this way. While the electric field is still that way, now the angle is 90. Cosine of 90 is 0, which means there is no electric flux passing out through the curved surface. So we only need to consider the two flat surfaces. And then this is Gauss law. Closed surface integral E dot dA is Q by epsilon naught. Let's look at the left-hand side. E is a constant. We're trying to find the electric field at this point. So it can only have one value, right? So take that out of the integral. And all we have is integral dA, which will give you the total area of the surface. Let's just say that the total area of the surface is dA. So you have one surface here, and you have another flat surface on the other side. So the total area would be 2dA. So E dot 2dA is equal to Q by epsilon naught. Now we're going to define the surface density of charge. I know it's called sigma. Because the charges are on a surface, it's a plane sheet. So we're going to say sigma is the total charge divided by the area. So whatever is the total charge here, because we only consider the charge enclosed by the surface, right? So that means if the total charge is Q here, and we know the total area is dA, sigma is Q by dA, which means Q is sigma times dA. I know I didn't write it, but I think you can understand. Sigma is Q by dA, so Q is sigma times dA. And now the dA's get cancelled, and you get E is equal to sigma by, this 2 swings to the denominator, so you get sigma by 2 epsilon naught. Wow, what a formula. That means the electric field is independent of the distance. Did you notice that? So we could be trying to find the electric field here, or maybe here. Doesn't matter. As long as this is an infinite plane sheet of charge, the intensity is the same at these 2 points. And it's given by sigma by 2 epsilon naught. So that is the intensity due to a plane sheet of charge. And now the question is, what if we have 2 sheets of charge kept very close to each other? Let me tell you, this is the capacitor. So we are going to get the formula that we will use later to find the capacitance of what is called a parallel plate capacitor, where you have 2 plane sheets. Now they are not infinite, but we're going to approximate the formula and say that If the distance is really small, then even a small area could be considered to be infinite, because it's always a comparison. So that means if you're trying to find the field really close, even this area could be regarded as infinite. I hope you got that. So let's go there. So what if you have two plane sheets? Where is that? Okay. So let's find the field due to two sheets of charge coming up now. So those are the two sheets. Imagine one plate is positive, the other is negative. Because by electrostatic induction, if one plate is positive, the other automatically becomes negative, right? Or it could be charged by connecting it to a battery. We'll get there soon. But just imagine, one plate is positive, the other plate is equally negative. That means their sigmas are the same. We want to find the electric field first outside the plates and then inside the plates. Finding the electric field outside is really easy, because due to this positive plate, the electric field here is going to be outwards, but due to the negative plate, the electric field here is going to be to the right. And since both are going to be sigma by 2 epsilon naught, they will cancel out. Let me write it. So this is sigma by 2 epsilon naught, that's minus sigma by 2 epsilon naught, and you get, I'm moving too fast, and therefore it cancels out. That means there is no electric field outside these plates. Same thing here, because that's also equally outside, right? But what if you consider the electric field here? Now, take a look. The field here, due to the positive plate, is to the right, and the field due to the negative plate here is also to the right. So instead of cancellation, it doubles. That's why we get the electric field between the plates to be sigma by 2 epsilon naught plus sigma by 2 epsilon naught, which becomes sigma by epsilon naught. What is sigma? Sigma is Q by A. In this case, A is the area of the plate, Q is the total charge on that plate. So this is the electric field intensity due to two plates that are oppositely charged. And I'll leave it to you to figure out how the electric field would be if both plates had the same charge, like if both were positive or both were negative. I'm not even going to talk about it. I just want you to figure out how it would change, how the situation would change. All right. Cut.